Hello everyone, and in this video we're looking at Newton's laws of motion, the three famous statements which represent key relations in mechanics. That's the physics of moving objects. So, by now you have probably encountered this fellow, Isaac Newton, one of the most famous scientists in history. Although we have to remember he was just one in a necessary chain of many scientists. He doesn't stand alone. And in fact, he himself said, "If I have seen further than others, it is because I have stood on the shoulders of giants." Wonderful quote there from history. So his laws of motion described the universe perfectly for us until Einstein came along and realized there was more to the story. And now we know that his laws are really more of an approximation with large objects, and then we need to think about other factors as things get really small. However, it doesn't reduce their effectiveness in everyday life. That's exactly what we see on the macroscopic level. So we can still make use of Newton's laws even today. So we'll get right into the first law of motion, and I'm going to define both laws formally and then in a slightly less formal sentence. So Newton's first law of motion describes how an object moves when the net force on it is zero. So formally it says if the net force acting on an object is zero, the object remains at rest, or if the object is already moving, continues to move in a straight line with constant speed. So to say that in a slightly more simple form, an object will continue to move with the same speed and direction unless some external force acts upon it. So this is the statement of Newton's first law of motion. So, an example of the first law: if you are floating in deep space on a small asteroid that is not moving, you can pick up a rock and throw that into space, and because the asteroid is small and has no real gravity and there's nothing else nearby, that means the rock will just continue to fly through space forever without changing its motion until it falls into a sun millions of years in the future, but that's another story. Now though, let's think about an example from the real world, and if we think about standing on a skateboard with this very simplistic diagram, then a pushing force can start you moving, and you will continue to move even though the force is gone, but over time you will slow down. So why is it that you slow down? Newton's first law says that you should continue moving forever. But in actual fact, there is another force acting on you, and this force, you might have heard of it, it is called friction. So if there was no friction, with Newton's first law, you would not slow down, you would just keep rolling forever, although technically there is such a thing as air resistance, which is like friction with the air, so that is low at small speeds, but still there. So, as we just saw, every day you see moving objects stop, and this is because of friction. Newton's first law would have them keep moving, but because there is always some energy lost because physical objects touch other physical objects, that means friction comes into play. It is a force that resists sliding between two touching surfaces. It just moves in the opposite direction of the motion. So we can reduce friction by making surfaces smoother and more slippery, and that makes it harder for the surfaces to catch on each other. But friction, as far as we can tell, will always be more than zero under normal conditions. So we're going to look at the different types of friction now, and we're going to look at them generally, but do remember that each type of friction we mention here has its own mathematical treatment, and some of them are very different from each other. The first one we're going to look at is static friction, and if you've ever tried pushing something heavy like a refrigerator, you may have noticed that at first it was hard to get it moving, and then as you push harder, the object suddenly starts to move, and then it becomes easier. So when you first start to push, there is friction between the refrigerator and the floor opposing the force that you are exerting, and so the net force is 0. So static friction is the name we give to the force you need to give to make the object start moving. So when you push an object, the friction while it is not moving is actually higher until you reach the threshold of motion. And then once the threshold has been reached, the object moves and kinetic friction comes into play, which is actually a little bit lower than static friction. And you can see on the schematic there's 0 newtons at first, and then the force goes up to about 6 newtons, and then it suddenly goes down to somewhere around 3 newtons, because once the object starts moving, it's easier to keep it moving. You could think maybe about a person on a jet ski skimming over multiple waves. The bumps are less of a problem because they are going so fast. So we also saw kinetic friction on the last slide, and as we said there, kinetic friction is the frictional force between two surfaces that are moving over each other. And both kinetic and static friction can change depending on the surfaces. As we said, if the surfaces are smoother or more slippery, then the friction, what's called the coefficient of friction, will be lower, so the frictional force is lower. Notice there that kinetic friction is also called sliding friction, and as we said, the effect of kinetic friction is less than static friction, which is why it's easier to keep an object moving. But it is still a force that acts against motion, so if you want to keep moving that object, you must keep applying a force that equals or exceeds the kinetic friction. The principles of friction can also apply to fluids and rolling objects. In the case of fluids, liquids and gases are not the same as solid objects, but there is still an impact between molecules of liquid or gas against an object. And we saw an example of this in the case of air resistance. So there are rules for fluid friction, the friction of non-solid substances. And then there's also rolling friction, which is the way that wheels and other rolling objects move. Rotational physics is always slightly different because of the angular nature, and we'll see a few examples of this when we look at energy. But the principle is always the same. Friction acts against the motion of the rolling object, slowing it down over time unless force continues to be applied. So here we go on Newton's second law of motion, and this is the one that most people seem to know by the very famous equation. Think about a shopping cart at your supermarket. When you start shopping, they are pretty easy to control. That is, to change the direction and speed of their motion, but as you start to fill it up with shopping, it gets harder and harder to control. Why is this? So what Newton's second law does is describe how a force changes the movement of an object, and as we can see, one of the important things about the object is its mass, so heavier objects are affected differently. So when a force acts upon an object, the object experiences an acceleration that is proportional to the mass of the object. So another way of saying that is the effect of a force will depend on the mass of the object. The way that an object changes its motion will depend on its mass compared to the size of the force. So here it is, the famous second law equation, and what it does is connect force, acceleration, and mass. According to the second law, an object acted on by a force will accelerate in the direction of the force, as long as that force is not balanced by another force, of course. So acceleration is force over mass. You can see at the bottom with acceleration in meters per second squared, and the net force in newtons, and the mass in kilograms. So remember that ms to the minus 2, and that's seconds to the minus 2, is the same as m/s to the 2. And you can see off to the right there is a triangle of physics where you have the three letters F, M, and A. And the most common form of the equation is F equals ma, force equals mass times acceleration, which is a commonly used form for the equation. So let's just stop to review the units of force. As we know, force is measured in newtons with a symbol of capital N. It's an interesting point that a capital letter is used when the unit is someone's surname, a famous scientist from history. So because the SI unit for mass is the kilogram and acceleration is meters per second squared, that means that 1 newton is equal to 1 kilogram meter per second squared. And remember, as we said before, meters/second squared is the same as saying meters seconds to the minus 2, because x to the minus 2 is 1 over x squared. X to the minus 1 is 1 over x. So this is what's called a reciprocal, 1 over something. Something to the power of minus 1 is the same as 1 over that thing. Although it does make units ever so slightly confusing. Let's ask a couple of quick questions about the second law. A book with a mass of 2 kilograms is pushed along a table. If the net force on the book is 1 newton, what is the book's acceleration? So remember, this is the net force. This is after all things like friction and everything have been calculated in. The net force is 1 newton. And if you've finished with that, then try a second one. A baseball has a mass of 0.15 kilograms. What is the net force on the ball if its acceleration is 40 meters per second squared? So now we're going to take a look at gravity, and again it's going to be a review of the basic concepts rather than a detailed mathematical look, although we're going to look at it in more detail than the different types of friction. So the force of gravity exists between any two objects that have mass, and it's always attractive, so it always pulls the two objects together. As far as we can tell, gravity has infinite range, so the gravitational attraction between any two objects in the universe is greater than 0, no matter how far apart they are, which is a pretty mental concept when you think about it. So, additional details on gravity. The acceleration caused by gravity is proportional to the mass of the object and inversely proportional to the distance between them. And now's a good time to just quickly look at proportionality. There's the little symbol, the little kind of unfinished 8. And this means that there is some kind of multiplying relationship between these two quantities. It isn't necessarily directly multiplying, but it means that the relationship should scale according to a simple multiplication. Inverse proportionality, on the other hand, means that the values are related reciprocally. In other words, in this case, the gravitational force is inversely proportional to the distance between the objects, so it's proportional to 1 over d. And the equation that governs this is called Newton's law of universal gravitation. And in fact, you can see on the bottom is r squared. It's the square of the distance. So gravity gets weak very, very quickly as objects get further away, but it never ever quite goes to 0. Anyway, that's all we're going to say on gravity, although I'm sure you will come back to it in more detail in a later course. So we're going to stop there for this video, but in the next part we're going to continue looking at the effect of gravity on Earth and the way that some different types of motion actually work. See you there!